Imagine a cosmic waterfall, a cascade of space-time itself. The event horizon is its very edge, the precipice. Once you tumble over this invisible boundary, there is simply no climbing back out. Not even light, the fastest thing we know in the entire universe, can escape its tremendous grasp. This isn't just some imaginary line we draw in space, it's a fundamental frontier. It's a one-way door to the unknown, a place where the familiar rules begin to fray. Understanding this boundary is absolutely key to unlocking some of the universe's most profound and perplexing secrets, waiting patiently for us to discover them. The significance of the event horizon cannot be overstated. It is, quite literally, the defining feature of a black hole. It marks the ultimate point of no return. Anything that crosses this threshold, a spaceship, a planet, a beam of light, is forever trapped. It's a concept that stretches our imagination, pushing the boundaries of what we thought was possible. Think of it as the black hole's surface, though it's not solid like a planet's. Instead, it's a boundary in space-time itself, a silent guardian of the mysteries hidden within its depths. It's where the known universe ends and the truly bizarre begins. Our journey to understand these cosmic beasts began over a century ago. It started with Albert Einstein's revolutionary theory of general relativity in 1915. This theory reshaped our understanding of gravity, not as a force, but as a curvature of space-time caused by mass and energy. Shortly thereafter, a brilliant physicist named Carl Schwarzschild found a solution to Einstein's complex equations. He did this while serving on the front lines of a war, a testament to the human mind's power. His calculations predicted these strange objects and, crucially, pinpointed the location of this very event horizon we now discuss. So, what would an event horizon actually look like if we could somehow observe it safely? It wouldn't be a fiery wall or a shimmering barrier. Instead, it's the edge of a region from which no light can escape. This means the area within the event horizon would appear perfectly black, a true abyss against the backdrop of stars. Any light from behind the black hole would be bent around it by its immense gravity, creating a distorted, halo-like effect. It's a stark visual representation of gravity's ultimate triumph over all other forces in the cosmos. To understand the event horizon, we must first grasp the concept of the Schwarzschild radius. This isn't just an arbitrary number, it's a critical calculation. It directly defines the size of a black hole's event horizon. Named after Carl Schwarzschild, who we met earlier, this radius depends entirely on the mass of the object that has collapsed. The more massive the object, the larger its Schwarzschild radius, and therefore the larger its event horizon. It's a simple, yet profoundly powerful relationship. This radius tells us precisely where the escape velocity equals the speed of light, an unimaginable speed. Let's consider some examples to really appreciate this scale. If our sun, a fairly average star, were to collapse into a black hole, its Schwarzschild radius would be tiny, only about 3 kilometers, or roughly 1.86 miles across. Imagine all that solar mass crunched into a space smaller than a small town. For Earth, it's even more minuscule, about 9 millimeters, smaller than a marble. Now picture a supermassive black hole, like the one at the center of our Milky Way galaxy. These behemoths have masses millions or even billions of times greater than our Sun. Their Schwarzschild radii can span millions of miles, truly cosmic proportions. The gravitational forces at play near this Schwarzschild radius are almost beyond comprehension. As you approach this boundary, gravity doesn't just get stronger, it gets exponentially, terrifyingly stronger. It's this intense gravity that dictates that the escape velocity, the speed needed to break free, becomes equal to the speed of light precisely at the event horizon. Since nothing can travel faster than light, according to Einstein's theories, nothing can escape once it has crossed this critical threshold. It's the ultimate cosmic prison, forged by gravity itself, a force that shapes the universe on its grandest scales. This radius, therefore, isn't just a measure of size, it's a measure of destiny for anything that ventures too close. It dictates the boundary of the observable universe from within the black hole. For an object approaching a black hole, the Schwarzschild radius represents the point where its fate is sealed. Understanding this radius is fundamental not just to black holes but to our understanding of gravity itself in its most extreme manifestations. It's a key piece of the puzzle in our cosmic quest to understand the universe's most enigmatic objects and the laws that govern their very existence. Imagine you are watching a brave or perhaps foolhardy astronaut journey towards a black hole. From your safe vantage point far away, you would witness some very strange phenomena. As the astronaut's ship nears the event horizon, the light from it would become increasingly stretched to longer, redder wavelengths. This is known as gravitational redshift, a direct consequence of the black hole's immense gravity warping space-time. The ship would also appear to dim, its light struggling to climb out of the deepening gravitational well. It's like watching a friend descend into a deep, dark valley, their voice growing fainter. Furthermore, time itself would appear to behave bizarrely from your distant perspective. Clocks on the approaching ship would seem to slow down, ticking more and more lethargically as they get closer to the event horizon. This is called gravitational time dilation. As the ship reaches the very edge of the event horizon, time for the astronaut, from your point of view, would seem to grind to a complete halt. The ship would appear frozen in time, hovering at the brink, never quite crossing. It would fade from view, redder and dimmer until it becomes invisible but never seen to actually enter. Now let's switch perspectives. What about the astronaut falling into the black hole? For them, the experience would be dramatically different, especially if it's a supermassive black hole. Surprisingly, they might not even notice the exact moment they cross the event horizon. For a very large black hole, the curvature of space-time at the horizon itself can be relatively gentle. There's no signpost, no dramatic jolt. They would simply pass from a region where escape was possible to one where it is not, without any immediate local indication of this monumental transition. It's a silent, subtle passage into the unknown. However, the type of black hole matters immensely for this initial crossing. If our astronaut were falling into a smaller, stellar mass black hole, things would be far more violent even before reaching the event horizon. The difference in gravitational pull between their head and their feet would become enormous. This tidal force would stretch them thinner and thinner, like spaghetti, a process gruesomely termed spaghettification. For supermassive black holes, these tidal forces at the event horizon are much weaker, allowing for a potentially gentler passage across the boundary, though the ultimate fate remains the same deep inside. Once an object, or our intrepid astronaut, crosses the event horizon, what lies beyond this cosmic veil? Deep within, at the very heart of the black hole, lies the singularity. This is a point of theoretically infinite density, where all the black hole's mass is crushed into an unimaginably small volume, possibly even a point with no volume at all. Here the fabric of space-time curves infinitely. The laws of physics as we currently understand them simply break down. We don't have the equations to describe what happens at the singularity. It's one of the greatest unsolved mysteries in science. The fate of any matter that crosses the event horizon is ultimately to be drawn towards this central singularity. While an astronaut might cross the event horizon of a supermassive black hole relatively unscathed initially, the journey doesn't end there. As they approach the singularity, the tidal forces, even in a supermassive black hole, would eventually become overwhelmingly strong. Spaghettification would then become inevitable, tearing apart anything and everything into a stream of fundamental particles. No structure, no information as we know it can survive this ultimate gravitational compression. It's a one-way trip to oblivion. This raises a profound question known as the information paradox. If information falls into a black hole, is it lost forever? This seems to violate principles of quantum mechanics. The late Stephen Hawking proposed that black holes are not entirely black but emit a faint glow, now called Hawking radiation. Some recent theories building on his work suggest that information might not be entirely lost. Perhaps it's subtly encoded in this radiation or imprinted on the gravitational field. The debate continues, pushing the frontiers of theoretical physics, trying to reconcile gravity with the quantum world. Understanding event horizons and black holes is crucial for many reasons. They are not just cosmic curiosities, they are fundamental to the universe. They shield us from the singularities within, yet their influence shapes galaxies. Studying them helps us test the limits of general relativity and search for a theory of quantum gravity. The Event Horizon Telescope has even given us images of the regions around them, turning theory into observation. These dark enigmas hold keys to understanding galaxy formation, the evolution of the cosmos, and perhaps the ultimate fate of the universe itself.